Stanford University. And later he was appointed to work in a pretty impressive number of major physics laboratories of the United States, including but not limited to Los Alamos, the LBNL, Jefferson's Lab. He worked in Columbia University, and since 2000 he is endowed professor at Hampton University, and since 2002 he's a director of the NSF Physics Frontier Center for the study of the origin and structure of matter. Also, since 2001, he's participated in the Harvard University Visitors Committee, and in 2002 he joined Yale University, and he works with Atlas Experiment, and his main domain is pixel detectors, leaning towards experiment, and leaning towards data analysis. It's dark matter searches. And today he will talk about the dark sector searches with Atlas Experiment, exploring the Higgs Particle-like scenarios. Let's welcome Dr. Baker.
Thank you. So it's a real pleasure to come here. I grew up in Arkansas, and I have family in Texas, including my wife is from Texas. And I've been here. I've been here for 15 years. So it's wonderful to come back. So I wanted to talk about the Higgs boson as a portal to a so-called dark sector. I'll motivate it, and then I'll show you the studies that we have made so far and our plans for the future. So what we do as particle physicists, as you already know, is we ask questions about nature at the most fundamental level. What's the world made of? What holds us together? And where did we all come from? And we try to use particle physics as a tool to understand this. So in this quest, over the past 100 years or so, we've developed, we meaning collectively, the experimentalists and the theorists, have collectively developed this standard model. And it's a combination of quantum mechanics and the special theory of relativity. So in this standard model, it's been called the most successful theory ever developed. It describes our world over the highest energy scales, the largest energy scales, and from low energy physics to the highest energies that we can achieve with our accelerators. It also describes our world over time scales, various we can actually, with the standard model, understand processes that happen in 10 to the minus 25 seconds all the way up to the age of the universe. We can project back to the very beginnings of our universe using this. The standard model includes these quarks, and it includes these leptons. These are all spin-and-a-half particles. It also includes, for example, these force carriers. So it's a wonderfully successful standard model. It's a crowning achievement of 20th century physics, and it's been tested thousands of times in all our experiments. All of our experiments to date that test the standard model, that are designed to test the standard model, are in excellent agreement with the theoretical predictions and postdictions. So there's a problem. The problem is that in order for the standard model to work so well, the particles in it had to all be massless. And yet we know nature gives us that particles have mass. So what was the mechanism to give particles mass so that the standard model can work so well and we can have such a great description of our universe? So one proposal was the Higgs mechanism, the Higgs boson. There were competing proposals having to do with extra dimensions and boundary conditions and warp extra dimensions, and there were other possibilities. So the Higgs mechanism was thought to be the most popular and perhaps the most theoretically well motivated, in my opinion. So a most basic question was always, why do particles have mass? And more than that, why is there such a disparity in masses? Why is it, for example, that the top quark at 175 GeV is so much heavier, for example, than the electron, which is like a half MeV, or some of the lighter quarks? So this Higgs mechanism predicted the existence of a new elementary particle, the Higgs particle, that mediated some Higgs interaction, this Higgs field. So people had searched for it for decades at accelerators, but it wasn't until the LHC was built. The LHC was always thought to be venue for discovering this new particle that was predicted by, most of the credit goes, I think, to Peter Higgs and Francois England, but I think there was maybe one or two other people that were involved in it as well. So that was the search for looking for the Higgs boson. So this motivated it once this is why the LHC really was built. So in order to make this discovery, you needed powerful accelerators that accelerated protons, for example, to extremely high energies and brought them into collisions with each other and other particles. We needed really wonderfully built precision detectors. These detectors had to be the size of, for example, 3-story buildings, and they had to have all of these different components working together, and yet we had to track and understand particles that at precisions of, for example, in distance were the width of a hair, a human hair. We also needed not just accelerators and detectors, we needed computers, and not just computers. We needed to collect and store and distribute and analyze all the vast amount of data that was coming in at the LHC. We have colleagues on both Atlas and CMS, for example, here at Texas A&M. So you're in College Station. We have colleagues in France, in Germany. We have colleagues in Australia. We have colleagues all over the world, and we all need to be able to access the data and analyze it in a seamless manner. And without this computing grid, this would not have been possible, because in fact, some of the Monte Carlo events that were simulated with Monte Carlo could take up to minutes per simulated particle, and we had to have millions of these. So this is also enabled it. And then finally, we had to have a group of really bright people. In my opinion, even with all of the technology, still the most impressive part of working in this collaboration is working with the people. And I also wanted to point out, especially for the young people here, the worst part of being in this collaboration can be working with the people. Everybody thinking they're, the smartest people on the planet. They're not. Okay, so I wanted to show you also the Atlas detector. Since this is a CMS institution, you've seen the CMS detector, but Atlas is, it's probably larger in volume than CMS, if I understand it, but CMS is heavier. So I'm told that if you were to drop this in the Atlantic Ocean, it would float. I don't know if that's correct or not. And then you see the size of the people here. Now, without going into details, I just wanted to point out the collisions happen here in the center, and the first particles to detect the remnants of these collisions is the inner detector that included silicon detectors and this transition radiation tracker, and then there's a solenoid, and then there are the calorimeters, and then there are the muon chambers on the outside. So I show you that simply to point out that I'm shameless about this. My group was the one who helped to build this barrel transition radiation tracker. This is when I was at Hampton University, and we built it on time and on budget, and we had it installed, and it worked just fine. So given that now, we started this hunt for the Higgs boson. So this is just a time-elapsed sort of rendering of how the data came in and how it compared to what was expected. So this data, this includes both the 7TeV data and the 8TeV data, and it shows how it worked as we accumulated more and more events in the different runs. And this is what we saw in this data. So what is it? So first of all, we needed something to act as a calibration. Because we didn't know exactly where the Higgs boson, we didn't know its exact mass, we didn't know where actually it was going to show up. And it was a large region of sort of, in this case, the decayed into 4 leptons is the I should have pointed out. So this TRT, this transition radiation tracker, was especially useful in separating leptons from hadron, hadrons like pions especially, and also kaons and other heavier particles. So what we did was this TRT not only provided tracking information so we could get momentum determination, but it also provided this special particle identification as well. So It was the 4 lepton channel that, since we have to build the detector that would help us to distinguish electrons and muons from pions and kaons and other kind of things, it was natural to use this channel to search for the Higgs boson. So the first thing we wanted to do, you had to understand, you had to have some kind of calibration to show that you could detect 4 lepton events and determine a resonance there, because in the end we're going to look for this resonance. So if you want, for example, to look at Z bosons, the Z obviously only decays into 2 bosons, but in a process like this, you can have the Z, one of the leptons radiates a photon. This photon then converts into a lepton-positron pair. And then along with the other 2 from the Z boson will give you 4 leptons, and this is the peak you see here. Additionally, we also have, when the mass range is high enough, above sort of 180 GeV, you can have 2 Z bosons that are both on shell. And that's what this region is. And you can see how it compares to the data. So this is the background from ZZ or ZZ star. That's what this is. This is the other backgrounds are very small. The Z plus jets and TT bar, these are all small compared to these. The major backgrounds is the ZZ star and the ZZ going to 4 leptons. So finally, we were able to see this peak at in the vicinity of 125 GeV. And this is the thing, this was one of the discovery channels in both ATLAS and CMS, the Higgs to 4 leptons, along with the Higgs to gamma gamma. So obviously, this was a big hit. And even though I was one of only 7,000-ish people that discovered it, it was just a wonderful feeling to be a part of a new discovery. We now know how elementary particles get their mass. So it appears that nuclei get their mass from the binding energies, the binding energy of these nucleons in the nucleus that give the nucleus its mass. And the quarks that make up the nucleons have mass. We know how it is that nuclei get their mass, and therefore molecules get their mass, and then you work your way up the food chain all the way to how we exist. We did not know how elementary particles got their mass until now. We now know the answer to that, assuming, and it looks like it's possibly the case that what we've seen is the standard model Higgs boson. So by an analogy, if, for example, I don't know who's the most popular person in this room. Let's say you're president. If your president was to come into this room, we would all crowd around him and want to meet him and touch him. And so he'd have a hard time, getting through this room to come up here to give a talk, whereas when I came in, nobody cared. I just walked right up to the front of the room, right, and gave a talk. So this is, by analogy, the way the Higgs mechanism works. As elementary particles, so all of space is permeated by this invisible field, this Higgs field. Particles that pass through it, depending on how much they interact with it, that's how they get their mass. So photons, for example, are massless, so they just pass right through this Higgs field, whereas electrons have a smaller mass than the top quark, and it interacts not as strongly as the top quark, but more so than the photon. And then the top quark interacts very heavily with this invisible field. So this is how particles get their mass. And it won these 2 gentlemen the Nobel Prize in 2013. And again, I'm sure some of you may feel the same way. Just the fact that ATLAS and CMS were mentioned, that's a good feeling. That's how my connection to the Nobel Prize, which would probably be the closest I'll ever get in my life, but it's still fun. So now we know the standard model is complete. Here's what the standard model consists of. It consists of 36 quarks, 8 gluons, 6 charged leptons, 3 neutral leptons, 4 gauge bosons, the Z, the W plus and minus, and the photon, and the Higgs boson now that it has been discovered. So we know that there's a total of 58 known elementary particles in the standard model, right? And the standard model only describes this small slice of the matter in the universe, which I'll come back to. Sometimes those that aren't in the field will ask, well, what about gravity? How can you say this is so successful if it doesn't include gravity? And the answer is, it was never designed to describe gravitation. The standard model wasn't meant to describe electromagnetic and weak and strong interactions, not gravity. It's like the theorists at Yale tell me that blaming the standard model for not incorporating gravity is like blaming your toaster oven for not giving you orange juice. That's not what it was designed to do. But what it was designed to do, it does extremely well. So, why do we still go to the LHC? If the Higgs has now been discovered and the Standard Model is complete, where do we go next? Why do we believe this isn't the only discovery that lies ahead? Well, it's because most of the universe, so the Standard Model only includes this small sliver of the total matter energy budget of the universe. We don't know really what dark matter is, although we've known about the existence of something that we call dark matter for decades. So there are some ideas, some clever ideas of what it may be, but we still don't know for sure. And we really don't know what dark energy is, whether it's some property of space itself, or whether there are particles. In the quintessence models of dark energy, there are particles associated with this. So what is this dark matter? What is this dark energy? There are other questions, like at the beginning of the universe, right? The universe, as we know, started as some kind of a singularity. The singularity, it was right after this, so if you go forward in time, this small region of space, this singularity, began to expand, right? And the universe began to expand at a really rapid rate during this time of inflation. As it expanded, the universe cooled. This energy, mainly energy and particles, then began to coalesce at some point and form atoms, and then once atoms were formed, photons could freely stream through here, and all of these other particles coalesced. The quarks and gluons in this soup coalesced into nuclei, and here we are today, sort of 14 billion years later. So the point is, the antimatter question simply means, why is it that if matter and antimatter were created in roughly equal amounts, why do we exist at all? Why didn't they annihilate? In all of our experiments, in all experiments we do, whenever we create a particle, we also create an equal an antiparticle. So why is it, what caused the matter and antimatter to separate? And there are other questions as well. I just want to name a few. But this motivates what we call a dark sector. It's, in my opinion, it's a catchphrase for anything that's not non-standard model. This is what I'm calling the dark sector of physics. So what are its properties? It's non-luminous. It looks like it only has feeble interactions with the standard model particles and fields. The fact that 4% of the universe has 58 elementary particles associated with it means that it's naive to think that 23% that, or the sort of 90-some% of the universe that is dark matter and dark energy can only have one component. There's probably lots of different components to this, both dark matter particles, perhaps dark matter messengers that mediate the interaction between these dark matter particles. But whatever this is, the dark matter dominates the matter budget of the universe. So now the question becomes, how do we look for it? The only thing we have at our disposal, other than telescopes, the only tool that we have are other standard model particles and fields. So how can we look for dark sector if it has feeble interactions with standard model particles and fields? How can we look for this dark sector? So there's lots of reasons to believe in it. So what I will call a hidden sector, a dark sector. There's motivation from astrophysics, for example, and the satellite data. And some people say that this electron excess or this lepton excess seen in cosmic rays where there's no proton excess could be evidence for some dark force mediator. There's also motivations from just theoretical arguments about extra U1 gauge bosons, hidden sector and dark sector, some motivated by string theory. They're not predictions, they're just motivations. So you probably do the same thing that I do in my classes. When I talk to my students about the Higgs, I remind them that after Galileo discovered the telescope was invented so that they could look out in the oceans far away and tell if there was a ship coming to attack. Galileo pointed this new tool at the moon and discovered mountains on the moons and discovered moons of Jupiter. The point is, with the new tool, there's opportunity. We now have a new tool. We have a new particle that couples to matter in a way that's unlike any other standard model particle. So what happens if there's some hidden charge associated with the dark sector such that the neutrinos, the electrons, the quarks, don't couple to it, for example, so strongly. What happens if there's some other kind of reason that we haven't understood up until now that prevents us from seeing it directly? Well, the idea then is now with this new tool, this new Higgs boson, maybe it can be a portal or doorway to this new sector, this hidden or dark sector of physics. So for example, the Higgs, we know now how it couples to it couples to the gauge bosons, the W's, the Z, and the photons. We know how this happens, and through the Euclidean interaction, how it couples to quarks and leptons. So it's possible this Higgs also couples to this dark sector or hidden sector. And this is the motivation for using the Higgs as this portal for a dark sector search. So this was something that I wanted to pursue it early on after the Higgs discovery. There were theoretical papers that pointed out there could be dark vector or dark pseudoscalar particles. There's also obviously dark fermionic. Dark matter is in the WIMP paradigm. These are fermionic dark matter particles. So let's see how we use this Higgs boson to look for dark sector particles. So first of all, the good thing is, if I look at the decay branching ratios of this newly discovered Higgs as a function of its mass, we see that the mass is actually in a pretty good place for us experimentally because it decays into all of these different final states. The Higgs decay to BB bar is the largest. The Higgs decay to Z gamma among current analyses, this is the smallest. There are also some that are smaller, I think like Higgs to BU, and obviously the coupling to electrons is going to be even smaller because the Higgs couples more strongly to more massive particles, elementary particles. So even though I think theorists would have preferred the Higgs to be heavier, the fact that it's light and it lies in this region is good for us experimentalists. The other thing is that we know, now that we know its mass, we've always known its coupling. If it's the standard model Higgs, it's coupling to these different final states is known with pretty remarkable precision. At this point, few percent uncertainties is not bad. And some of them have larger uncertainties, but this isn't bad actually. So we can look for this dark sector by, first of all, in my opinion, understanding how it decays into these standard model particles and starts to look for deviations from what is predicted and what you observe. And this was the strategy that we used. So why this channel as opposed to one of the others where you have all of these different possibilities? Well, I mentioned to you about, I helped to build a detector that identified electrons and muons out of a sea of pions and other hadrons. So this is one reason. The other is that it's the golden channel. You saw that the backgrounds are small and easily manageable. You have a peak in the inherent mass spectrum as opposed to missing ET or other kinds of processes involving quarks. So you have good resolution, and the Z star is allowed to propagate off shell. So this was necessary for this Higgs search because of its mass. There's some degradation in energy, resolution, but we're going to use that.
One is on shell, right? That's why we went for backgrounds. You showed that.
That's right. One is off shell, but I'm not sure that
One is always on shell.
Well,
one is always on shell.
I don't know
so
what about Atlas experiment, but in CMS, one is can be far off shell, and another one is not exactly on shell, but it's like from 60 to 120 GeV.
That's right. We use 62.
So plus or minus 30 GeV.
Yeah. The only thing I was going to react to was your statement. It's because one of them is off shell that the backgrounds are low. It's because we are able.
Because one of them is on shell.
One is on shell. That does help, right?
Yeah.
So the Z mass constraint helps it. That's correct. Okay. Point taken. You're exactly right. And in fact, so here's what I wanted to use. So gluon-gluon fusion is the major interaction that produces this Higgs at the LHC. At CDF it was QQ bar, but at LHC it's gluon-gluon fusion. This gives us Higgs, which nominally decays into a Z star and a Z boson. And then these decay into leptons, electrons and muons. What my group and I asked is, in our analysis, is it possible that this Higgs couples directly to some dark vector particle? Let's call it a Z dark. This is any kind of a vector particle that is non-standard model. So I generically call it Z dark. So we have the 4 lepton invariant mass in the final state that comes from nominally this Higgs decay. And then the other thing is, if, as you correctly pointed out, we want to use the Z mass constraint. We want to have one of these is an on-shell Z boson, and then we want to look in this channel to see, is there evidence for something that could be something beyond the standard model? So in run 1, we ask a simple question. Of all the events that reconstruct back to the standard model Higgs, of all the 4 lepton events, could some of those be due to some beyond the standard model vector particle? At least in run 1, that's the question we asked. And if so, what would it look like? So what we wanted to do is to, first of all, we only use those particles in the 4 lepton spectrum that reconstructed the Higgs boson. We cut on all of this other stuff out here. We use the mass window between 115 and 130 GeV in run 1. We only looked at those decays to electrons and muons, and in this case, when I show something like 2 muons and 2 electrons, what I'm saying is this is the leading dilepton pair, and this is the subleading dilepton pair. After we have identified those that give rise to the Higgs, we then identify the on-shell Higgs, the Z1. This is the on-shell Z that decays to 2 leptons. And this is what you have here. So this is the data, this is the ZZ star, and this other backgrounds here, Z plus jets and TT bar and all of that. So it stands out well, and there's a nice peak here. We use the particle data group value for the Higgs. The subleading dilepton is the one, Then, so after you identify the leading dilepton pair, then you have the off-shell Z star. The Z star is the dilepton pair that then has the next highest invariant mass after you've identified this Z0, this standard model Z. And I think this is what you did in CMS as well. So then you identify what is the next subleading dilepton pair. That's identified nominally with the Z star. But we're now starting, at least in run 1, the idea was if there is a Z dark in this, it would give rise to some resonance. This is not an off-shell dark Z. This would be an on-shell Z dark of resonance that couples to the Higgs, and then in the end would give rise to maybe some peak or some excess above backgrounds in the subleading dilepton pair. Notice also, this is important, the Higgs to ZZ star is a background for us. My students got a kick out of that. Soon after the Higgs was discovered, it became a background in our studies. So that's the idea. And you want to look at evidence for Higgs goes to ZZ dark to 4 leptons over all over Higgs goes to 4 leptons. So this Higgs goes to 4 leptons would include Higgs to ZZ star to 4 leptons and Higgs to ZZ dark to 4 leptons. So I show the Atlas and CMS data from run 1. And again, the statistics were limited, but we were able to make a search looking for some peak or excess above, some narrow or modest peak or excess above background. So here's some of the, here's some results. So first of all, in the models that I like, right, so there are different models. Some theorists say in their models this Z dark can couple directly to leptons. They can decay directly into leptons. That's especially useful in the Higgs to Z dark studies. I had a problem with that because for various reasons. I think I've been beat up enough now that I think those models where the Z dark couples directly to leptons is probably okay. But I had the question, if this goes directly into leptons, why wouldn't we have seen it at SLAC or at LEP or in some of our other accelerators? But okay, let's not get into that. The models that I like best are where this dark Z kinematically mixes. It either mass mixes or through kinematic mixing, the way neutrinos mix between neutrino flavors. It mixes and converts into a Z star, and that's what decays into two leptons. Because this is
This is a low mass
that's correct. It has to be
That's what
60
you're saying, you could have
GeV.
introduced it, like, E plus E minus is correct.
It would have been, so, right, exactly. Why wouldn't we have seen it at the left? Where it's
Well,
like-
the couplings could be, in many of these models, like in SSM, for example, right? This thing is, has a large singlet factor fraction. And you can actually only produce it if you first produce Higgs, because Higgs has mixing in it, that it has a component in the singlet.
Yeah, so
If
that's
you just look at the plus and minus, you won't see anything because couplings are incredibly surprised with these particles. Right? And some of the experiments they do is, when they take this electron beams, right, they rank them to some incredible intensities, right, and dump them on targets.
That's right.
So the reason they do that is because they're trying to get this possibly very, very, very small compact couplings.
Yeah, so that was the
So
argument
you
that
can
the
relatively
argument-
easily avoid various.
Yeah, those were the arguments that were made, yeah. So the idea is, and so for example, in the Higgs to Z dark to 4 leptons, you have a standard model Higgs that mixes with Higgs singlet, some kind, not a Higgs singlet, some dark Higgs or something. That dark Higgs then decays into 2 Z dark bosons, and each of those then decays directly into leptons. That's correct.
But what difference, like observational, whether it's just a Z dark or undergoes, something else, it's just like width of the, whether it's
That's correct.
in
So-
shell where you expect to go there.
That's correct. So if this is a resonance, a narrow width, a resonance of narrow width, then even though it couples to this thing, which has a rather broad and featureless spectrum, it still, it prefers to couple when its mass is very close to this dark. That's why you would expect some excess, because this thing is a resonance. As you go farther and farther away, as this mass starts to differ from this mass more and more, then that probability gets smaller and smaller. That's why you expect something that looks like a peak or an excess above the background. The other thing I wanted to say was, there are other details about this. For example, so this Z star decays in like 10 to minus 20 seconds or so, something that's very fast. Whereas we don't know anything about this, it could last a long time. So this may have been one of the other reasons why you would not have seen it in Z decays, because the Z would decay into these before it would mix with this Z dark, for example. But okay, the point is there are other arguments to be made. There's other discussion points, but this was the process that we looked at. So the first thing we would do is to look for its ratio to the standard model process. The Higgs to Z dark to 4 leptons to what is the standard model Higgs to Z star process. So we looked at the 95% confidence limit on this thing relative to the standard model process, and this is the observed limits, and these are the expected limits in the plus or minus 1 and 2 sigma bands. We also looked at the absolute branching ratio, not comparing it to the standard model, but can we see anything? How many of these 4 leptons did we see, and how many? And so, if we don't see any evidence for this, then that means we can also extract the absolute branching ratio, knowing the standard model branching ratio. We also put new limits on this ZZ dark kinetic mixing. And in those models where this thing mixes with this Z star, the kinetic mixing, we have the 95% confidence limit on that mixing parameter is a function of the Z dark mass. And again, in our analysis, we only go from sort of 12 to 15 GeV up to 55 GeV. Once you get above 55 GeV, it's hard to tell which are the leading and which are the subleading leptons. And if you go below this, there are issues with background. And I think in CMS, you all had the same limits, if I recall, sort of between 12 and 60 GeV. And then there's an addition to that, there could be mass mixing. That's the ratio of their masses. So you can have this mass mixing times the branching ratio, and we set some of the limits on those as well. So now, that was run
But
one.
What is your
Yes.
mass resolution? So I mean, looking at those plots, it looks like it's a huge GeV.
The mass
So that's
resolution,
like 5%.
yeah, sort of 10 to minus, 10 to minus 2, 10 to minus 3 or something like that. Delta T over P or something like that.
But
It was
the-
roughly-
the mass resolution. I'm just
Oh.
looking at the frequency of the bumps.
Uh-huh.
It seems like it's actually a few GeV. So C mass, it would be like closer to 1 GeV.
Yeah, so,
Well, it floats with more.
okay,
Wavy.
yeah, so it's a good question. So, there are several ways to analyze this, right? So, one, the way that, in the end, we decided to do was to use different templates. So, you could try to say, what if this Z-dark had a certain width, right? That varied with mass. Its mass gets, its width gets larger as you go to higher mass. You can simulate that by saying, what if it had a Gaussian distribution? What if it had a bright Wigner shape? What if it had a crystal ball shape? We did all of those, and in addition to that, we did a Monte Carlo we did a full Monte Carlo simulation at a few of these mass points, and then we can extrapolate between them. But the combination of the mass resolution and the backgrounds as a function of the dark mass gives this structure like this. It's a
So
combination.
that means, that you actually have large intrinsic widths coming from Z star that went into the
Correct.
limit calculation.
That's
You're
right.
actually looking for a bump, small
That's right.
narrow bump. You're actually looking for a pretty broad bump. It's
No, we were looking for a narrow bump on top of a broad.
But it's not very narrow. Because you
No,
said,
but,
this
yeah.
is increasing in the.
But so for a given mass, you have different backgrounds that you have to contend with.
Right,
As a
but
function of
this sort of, this is a signal limits, right? So the typical frequency gives you the resolution in mass for signal, right? This waves in the limit, they, characteristic frequency corresponds to the resolution of your shape of the signal, basically.
Yeah, but
If you have a bump that has the characteristic widths, the limit will go up, right? And if, say you expect a bump like this, right, and you see something like this, and then your limit will go up. If you see a single point going up, it will not go as much.
That's right.
You have-
Yeah, it depends on the Z-dark mass that you use, that's right.
So, but that means your signal model actually must have some intrinsic widths to it,
That's right.
which is significant.
Yeah, but that's at the level of like a GeV-ish. It's about, it's a little inferior, I think, to CMS, but of the same, roughly. And so what you do is, you do that as a function of mass every 5 or 10 GeV along here, and look to see, do you see something that's compatible? What would a resonance at 5 GeV with at 20 GeV central mass with the width of a couple of GeV? What would it look like here? What would it look like here? And then you look at the data, you have to subtract the backgrounds and look at the data, and this gives rise to that structure.
But how does your signal look like? You have a plot
Yeah.
that shows.
Yeah, it would be a 1 GeV peak like this.
So it is an arrow.
Yes.
No, but
Yeah.
you-
in the narrow width approximation that we use.
But you have to convolute it with a broad distribution, quite broad, like a few GeV widths of the Z prime, or Z star
No.
itself.
No. Then, if that was the case, then the signal shape would be broad.
Yeah, so injected signal can be anyone. It can be very narrow, but you have to convolute it with
it's either the resolution or the intrinsic, width of the signal coming from Z star. It seems, it's with the order of a few GeV. Looking at the
So-
exclusion plot, it looks more like, 3 GeV or something. Do you have a plot of actual signal?
I don't show it in here. It is in the internal note, which, this is one of the things. It took us 6 months to get the data, and yet getting through all the machinery and atlas things, editorial boards took 2.5
Yeah, it's
years.
the same.
But anyway, I want to come back to this. So what happens is, now, for a given window, a given mass window here, the Z dark, if it exists, would have to have the exact same kinematics as the Z star in there. Because these data points all have to reconstruct the Higgs. So that, and not only does the Higgs mass have, to be reconstructed, the Z1 has to be reconstructed. So that actually gives you sort of, it narrows the sort of wiggle room you have here in looking in this spectrum for Z dark. So a Z dark is a resonance that it's a single mass with a width of a GeV or so. And then the Z star is a bin. It's a bin in Z star that surrounds that mass, and it can be of the same width, sort of a GeV or so. But you see now, this should be featureless, right? There shouldn't be evidence for resonance in this subleading dilepton invariant mass spectrum analysis or CMS, right? But a Z dark should give that. And this broad thing, okay, it has this feature. You're asking though, so you're asking why isn't this smooth?
No, why is it not more frequent? If it's a 1 GeV width, you know, it should be.
We only did that study I talked about every, I think, 10 GeV we interpolated between. You don't want to do a full simulation every 3 GeV or 1 GeV all the way across the two.
Yeah, so maybe I can take this
Okay,
offline.
sure. Happy to.
I have
I'm
a
always
question.
especially looking
So
for
cannot you search for the Z dark through something else? So for example, like WW producing Z dark, like a straight, like a, you also have this BBF search for Higgs, so you can do the Z dark through WW.
That's right. So you're asking a question. That is correct. There are other ways to look for the dark Z. This analysis was not designed to look at it in that way. This analysis was designed to look for something that directly couples to the Higgs, not to some other standard model particle.
But it couples to Z, right? So that
Kinetically
means
mixed with the Z.
that means WW couples to Z, so WW is Z is Z.
Well,
So
if the coupling is incredibly small,
Well,
right?
how
Once
small
you
is-
produce the Z dark, it has no choice, it will have to go through recent decay.
Yeah. So that.
But if you just have the Z and coupling is very small, you will not see this.
Right. So that was one
How
of the things.
small of the coupling do you know? Was this?
Well,
10.
it's small. It's smaller than the limits that we set. For example, on this kinetic mixing. So, for example,
Was this coupling?
so it's less than 10 to the minus 1.
Yeah,
It's
minus
at
1.
least less than that.
Yeah, that of course you would have seen, yeah.
Yeah, we would have seen it. But the one thing though that I have argued, and you may not agree, in which case I hope you'll say so, because I'm always looking for new ideas. If this Higgs had so in those models where there's so you could ask, why is it then that the Higgs doesn't decay into a Z star here, and then the Z star decays, the Z star kinetically mixes with the Z dark, and then it decays into leptons. In some models, that's what happens. One argument I like to make is, this thing decays so rapidly that maybe it actually would decay here into these before it had a chance to mix with the dark Z.
Yeah, but then if the, I think it's a question of sensitivity. If this epsilon is really of the order of 10 to negative 1, you would have seen it, you know, like, I don't know, anywhere else, at the left, right? You know, that
Yeah, somewhere else, so
Well, no, that's the point that I'm making, and that is, that's how you probably would not have seen it, because at left, the Z star or Z that you would create would decay into leptons before it would
That
mix.
would require much smaller type of epsilons when those if you exclude it. That would require epsilons, I don't know.
No, it's the-
negative something
it's the-
much.
No, it's the lifetime. It's the
Right, but
lifetime.
it goes into lifetime, right? The coupling
Right.
gets very small.
That's right.
Then you can also develop a certain lifetime.
That's right. So I think, so the argument that I'm making is, you're saying this, if I flip this, this kinetic mixing is the same. This
No,
kinetic,
your argument is absolutely correct, but it implies that epsilon is very small. Because, you know, if
Is it?
epsilon,
No.
if
No, no.
epsilon is of the order of 10 to negative 1, you know, like, then this will not be, I mean,
Okay,
Center
so I hear what you're
one is
saying.
very large epsilon.
But let me push back on you just a little more, not because I'm being intransigent, but I like this because I'm trying, I think it helps me understand this better. So, now I forgot what I was gonna say. So, you're making the point that this kinetic mixing parameter, it doesn't matter if the Higgs couples with the Z and then it mixes with the Z dark that decays into electrons, or if it's the way that I show here, where the Higgs couples with the Z dark and then it decays into the Z star.
If you would go to lab, right, which produce like enormous numbers,
Z, right.
if the epsilon for the kinetic mixing of Z and Z dark is as large as right one, you would have seen a truckload of these guys in lab.
So that's the point I'm making, I think. And that is, why wouldn't you have seen it at left? Because in the cuts that we place in Atlas and in CMS, you have something like roughly 1 or 2 centimeter cut that says these leptons that come from this would have had to have decayed inside of this cut. And I think LEP and the other experiments at SLAC had the same sort of cut. It wasn't meters. In other words, you didn't expect a displaced vertex of meters.
Right, but to get
But-
to meters, this
but-
epsilon would have to be 10 to the
But-
negative 4 or something,
but-
or 5. Or,
Because the Z decays, it decays in 10 to the minus 23 seconds. It's tiny. This is like the size of an atom. You can increase that by 10 orders of magnitude. You can increase that all the way up to, this thing could have a lifetime of 1,000,000 times that of the Z star, and you still not be able to distinguish it in the cuts that you place in your experiments. Because the cuts are around 2 centimeters. I think it's like 2 centimeters in the longitudinal direction.
right,
and
but
1 centimeter.
that again implies explicitly, if you wanted to have the 1,000,000 times, it requires 1,000 times smaller coupling, right? To develop a lifetime, right, for this Z dark, to have a lifetime of escape detection, coupling needs to be very, very small. But the coupling levels that you are excluding in this analysis are 10 to negative 1. So I think your point is that lab would have probably been much more sensitive to
Actually,
this than Atlas.
Actually, no. If you look at the left limits, I think I show it later. We'll come back to it. The left limits are of the same order of magnitude. We're a little more sensitive at higher masses than left. I'll show you that. This is a good point, because this is also an argument I looked at. Are we more sensitive than left or SLAC? And I'll show that a little later, in just a few minutes, actually. So in run 2, we're going to have increased statistics. We also are going to use more sophisticated machine learning algorithms to look for a peak. We also can include a pseudoscalar search. It not only can decay into a ZZ dark, but the Higgs can decay into a Z plus a 0 minus particle, believe it or not. I didn't believe it at first either, but if you do the Clutch-Gordon, it works out. We're going to lower the Z dark mass. We're going to look for a lower Z dark mass down to roughly, sort of 10 GeV. We're going to look for something that is a displaced vertex, not meters, but sort of outside of what is what we call the standard model Higgs cuts to be placed on the decay of this boson that decays into 2 leptons. So it's Z dark. If our standard cuts are sort of 2 centimeters, roughly 2 centimeters, we can look for something that's a little beyond that. Sort of, what if we can bin our data? We have enough resolution to bin it, not in units of 2 centimeters, but in units of 1/2 centimeter. We can perhaps look for some evidence for a displaced vertex, looking for e to the minus t over tau kind of analysis. And the other thing, one of my colleagues said, why are you just looking for narrow width Z darks? Why not look for a larger width? Like if the Z dark propagates off shell, it could have a larger width. So now you just look for an excess above backgrounds. The models that I look at don't favor this Z dark that propagates off shell. Those couplings are supposed to be really small, but okay, it's a model. Okay.
Also, I have 3-body decays and stuff for it, then you will not have a lot.
That's true. That's correct. That's right.
So have a question. So the models you look at, don't they also have coupling with photon? Because Z dot at the end, fundamentally the B and A, and then when you diagonalize it should give you a Z coupling as well as a photon coupling.
That's right.
So how?
So at these masses, it really couples to hypercharge. That's right. If you go to very low masses, we'll call it a dark photon. At these high masses, I call it a Z dark. But that's right.
So that means, so wouldn't you end up seeing some photon out of this? That means if I end up reducing.
So the Z dark would somehow have to convert into photons. And it can do that through kinetic mixing. It can do that potentially in other ways.
Yeah. So what my point is, so when you reduce Higgs to Z dark Z, that Z dark would go to Z, but Z dark also can go to Z.
That's right.
So that means you have.
Yeah. But the point is that the point that I would argue is the farther in the larger the difference in mass between this and the vector particle that it couples, that it mixes with, the less likely that will happen. That's the argument. It's only when these are the biggest signal, the biggest effect you see is when these are very close in mass. So if this wants to couple to a photon, yes, that happens. And yes, that also happens. Believe it or not, I spent some years when I was at Jefferson Lab looking for the conversion of a photon into some dark particle, and then it would convert back into a photon. Yes.
So, and if I look at that picture, what's the constraint on epsilon from if you combine everything? Like from LHC, I can see that it's a 0.1, but suppose I open up that photons, also they would start contributing at that time. More intensity. So do you know what would be the constraint at that time?
Yeah, those become a little more difficult even experimentally because this Higgs would decay into something that has a. So you're saying that Higgs goes to gamma gamma, for example.
Yeah.
Then this thing would somehow couple into leptons in this analysis, but they would be so boosted that you probably wouldn't be able. It would be hard to separate them. There are studies of lepton jets in both Atlas and CMS. These lepton jets are highly collimated pairs of E plus E minus and dilepton pairs. It's hard to separate them. They look like they're just one lepton jet. And the lower mass that you go, the more difficult it becomes. But there are studies of lepton jets that go down to 1 GeV. And more generally, I would answer your question as follows. You're asking, aren't there different analyses? Aren't there different ways to do this? And the answer is yes. And I was simply making the point that in run one, we wanted to do something really simple.
No, that's fine. Yes, I was trying to understand what's the bottom line for this kind of epsilon mixing.
Yeah, I'll show you. Okay. So I just wanted to make the point about the luminosity in 2016 is much superior to what we got in 20 before, ATV and even previous years. And these new machine learning algorithms, perhaps I won't go into them, but there's the BDT, which is more powerful than the cut-based, and then there are these new deep learning algorithms that we use. And so look, I'll just come to the end, basically wrap this up. So these are what was shown in iChip. This is the Atlas and CMS results. We rediscovered the Higgs. There's a story behind that, which I'm going to. And this is in the mass range between, this is the number of events in the mass range between 180 and 170. In CMS showed between 70 and 170. And then this is when you look at a larger swath of invariant mass. So, we know we're back where we were, we've rediscovered it, and we're plowing ahead. Then if you look in the leading sublepton invariant mass spectrum in Atlas and CMS, what I call Z1, you see that you identified the Z, and this is with sort of 14 inverse femtobarns of data. And then we want to look in this subleading dilepton pair. So I'm a little concerned that if you look at these, the Atlas, we see these events that are sort of above the standard model prediction. So this is the Higgs decay to ZZ star, and this is a background here. We're going to look for, in a large width approximation, you don't look for a narrow width. You look for something that may be larger, 5 GeV, higher. And in CMS, they don't, the sort of data above background, this is the Higgs, the full electron, that's here. It looks different. So this kind of study may not be possible, is the point I'm making. I don't know. We'll have to study this. So I wanted to just end by showing you examples of some impact. So this is just one example. If I look at sine squared theta w, the Weinberg angle, as a function of the Q value of the process that was used to measure it, these are the atomic parity violation experiments on cesium. This is molar scattering, I think, at SLAC. This is the Q-weak experiment at Jefferson Lab. This is neutrino deep inelastic scattering and all of them. You see the error bars are rather large, but then these are projected new experiments. This is not where the data lies, it just is there to show you in red what the error bars are going to be like. So the error bars are shrinking, right? But already, there appears to be some indication that in some region here, that maybe, so this is the standard model prediction, and this is what the experimental data is showing. So there looks to be a 1.8, the analysis was done by Bill Marciano and his group at Brookhaven. There's like a 1.8, just almost a 2 sigma deviation above this standard model prediction here. And this is the SLAC at the Z pole here. So what he did was then to show what would happen if you had a dark Z of 15 GeV and one at 25 GeV. So it comes a little bit above this standard model prediction here. And so the data, it's not compelling yet, but the point is there is paying attention to this model. That's the point I'm saying.
No, he gets a 2 sigma deviation.
What you do,
side, right?
no, what you do is you extrapolate it.
No, I mean,
The first point.
it reduces tension there, but it increases tension on the left.
That's right. That's right. So there are arguments about there's another experiment that's going to be done on radium plus or something that's supposed to be more sensitive and better able to handle the theoretical. There's a large theoretical uncertainty associated with this. Understanding the atomic physics in these atomic parity violation experiments on nuclei like cesium. There are large theoretical corrections that have to be made, and this is one of the arguments that he was saying. This is why you want to go to a new nucleus with these kind of error bars. In addition to the systematics that we move this up or down, there's also shrinks this. It's more complicated than I'm making it sound, but I just wanted to point out.
But also science square theta, if I remember correctly, there was this discrepancy between the hadronic final states and leptonic final states. I think Marciano was kind of average everything. So, but there is also systematic in terms of what final states you achieve.
That's the CBB, right?
Yeah, something like, if I remember correctly. So once you take that into account, what the lower is, there is not much you can do at this time. It's systematic. So hadronic versus leptonic.
Okay, so first of all,
average,
if I understand your question, these are molar scattering experiments. The E158 is a molar scattering.
Yeah, but you also use the data and SLAC.
Oh, I see what you're saying, yeah.
Yeah.
These are, yeah, that's right.
So at the end, you are,
I see
so
what you're saying.
if they get a little bit lifted, then right away.
Yeah, but these are pretty much in agreement with the standard model, pretty much. These are extrapolated, these have to be extrapolated down here. Is what Marciano does. And this is where he gets sort of it's a small difference. It's like if you extrapolate down here, it becomes like 0.23 something like somewhere in here, as opposed to 0.232, which is the standard model result. But anyway, I should finish because of that. And so fine. So this was one of the papers I want to show. This is this kinetic mixing parameter as a function of the mass of whatever it is that you're talking about. So down here, it would be sort of, visible photons in sort of, I think, this range. These are limits set from different analyses. Solar lifetime, Coulomb interaction between two charges brought next to each other, Rydberg constraints, and we're way up here. These data didn't exist before. The theorists showed that it couldn't be sort of larger than this, and this is what it is. But we were the first to actually get this up, sort of in this range. And this is the mainly the left result, and then these are other fixed target issues. So you were correct that this mixing is between a dark vector particle that's like a dark photon at these masses, and up here it couples more to hypercharge. So I call it dark Z, but yeah, it's really coupling to the hypercharge. So that's it. That's it. And I just wanted to end by showing members of my group. So that's